So, discuss natin yung stress diagram on a pre-stressed concrete. So, this would show on how do we interpret the application of the compressive stress induced by the pre-stressing tendons. First, since we are applying an actual load to our beams, so let's illustrate the actual stress due to the pre-stressing tendons. So actual stress, this would be compressive kasi nga hinila natin initially muna yung mga tendons natin to transfer a compressive strength or compressive force doon sa beam natin. So that would be P. And to show this would be your stress diagram. So the stress due to the actual stress from the tendons would be negative since it is positive. Take note that we are considering the tension would be our positive. The next is the flexural stress. If the tendons if the pre-stressing tendons are located with eccentricity, so ibig sabihin wala siya sa neutral axis, and from if your beam is simply supported, we assume that the maximum moment would be located at the midspan. So if that's the case, we are going to put or place the tendons at the lower part of the beam, so that it would cause a flexural stress shown like this in the figure. So from this, you would notice na yung beam natin ay nag-deflect pataas since nga naglagay tayo ng compressive force galing sa bandang baba ng beam natin. So ang tendency, magkakaroon tayo ng initial displacement pataas. So this drawing, take note, is exaggerated just to show you the effect nung pre-stressing tendons natin. So take note that the eccentricity is the distance from the neutral axis papunta doon sa location ng applied compressive transferred compressive force galing sa tendons natin. Then from here, so dahil nga yung figure natin deflection pataas, lumilitaw na yung bandang taas natin is tension, so that would be positive, and then yung sa baba ay compression negative, and that would be equal to yung formula natin na pinakita last time. So the flexural stress is equal to P multiplied by the eccentricity multiplied by C, which is the distance from the neutral axis papunta sa pinakababa ng beam natin. And then lastly, since we are talking about structural beam, so for sure meron niyang loads, no? So kapag nag-apply na tayo ng loads, so magkakaroon din tayo ng flexural stress galing dun sa applied load na yan. So yung load na yun is pababa na, kaya ang beam natin magdi-deflect pababa. Okay. So ang mangyayari, yung taas na yung magiging pressure natin, and then yung sa baba na yung tension. So if you're going to draw the stress diagram, ayan. So yung taas, yun na yung negative, and then yung baba, yun na yung positive, which is equal to MC over I. So the flexural stress due to the applied load is equal to mc over I. So take note that yung moment of inertia natin is taken from the cross-sectional area of the beam. Sample problem number 1. A 200 by 400 mm PSC beam or pre-stressed concrete beam is pre-stressed with a final pre-stressing force of 500 kN at an eccentricity of 100 mm below the neutral axis. Determine the maximum moment that will produce no tension at the bottom fiber. For number 1, so we have a 200 by 400 mm pre-stressed concrete beam. And yung given natin ay meron daw tayong pre-stressing force that is equal to 500 kN, and that the pre-stressing tendons is located at a distance of 100 mm below the neutral axis. So ang hinahanap sa atin is determine the maximum moment that will provide no tension at the bottom fibers. So take note, no tension daw at the bottom fiber. So we have meron tayong concrete beam, so that is 200 by 400 by dimension. So we assume na simply supported yan. And then this would be your neutral axis. Neutral axis. Then yung pre-stressing force natin, P, which is located at the distance E, yung eccentricity natin, which is equal to 100 mm. So yung P natin is equal to 500 kilonewtons. So ang hinahanap natin, ang pinag-uusapan natin is the bottom fiber. So based doon sa figure natin kanina, doon sa illustrations natin, lumilitaw, syempre, of course, yung axial stress natin is always negative, so negative P over A. And then, yung flexural stress due to the pre-stressing tendons dun sa bottom fiber natin would be compression, so negative din. And then the flexural stress due to the applied force is positive kasi tension na tayo sa baba. So take note, sabi niya, no tension. So ibig sabihin, kapag walang tension, wala ding stress. So dapat equate natin ito na dapat yung total stress natin sa bottom fiber is equal to 0. So negative P over A, so that would be 500 kilonewton, so 500,000 divided by the area of the beam, 200 times 400, minus 500,000 ulit, multiplied by the eccentricity natin, which is 200 is yung C, and then 100 is yung E. So 100 E, then yung C natin is is 200, divided by the moment of inertia of the cross-sectional of beam, which is BH cube over 12, so 200 times 400 cube over 12, plus MC over I. So M multiplied by the distance C, 100, divided by, again, the moment of inertia, 200 times 400 cube over 12. So pindot. So your moment would be equal to 166 million. Yung unit natin dito is Newton mm. So kunin natin into kilonewton per meter. So 1 kilonewton is equal to 1,000 Newton 1 meter is equal to 1,000 millimeters. So you divided it by 1,000 twice. So lumilitaw that your moment, the applied moment must be equal to 166.67 kilonewton meter. Sample problem number 2. A prestressed rectangular beam 500 by 750 mm has a simple span of 30 meters and is loaded by a uniform load of 4.5 kN per meter including its own weight. The prestressing tendon is 225 mm from the bottom and produces an effective prestress of 1,600 kN. Compute and draw the fiber stress distribution on the concrete at midsection due to the axial force, prestress eccentricity, loads, and total stress. Number 2. So meron daw tayong beam that is 500 by 750 mm. And yung tendons daw natin is located 225 mm from the bottom. So say simply supported yan. Tapos meron tayong uniformly distributed load. So yan yung pre-stressing force natin. And then yung uniformly distributed load natin is equal to 4.5 kilonewton per meter. And then yung span natin is equal to 30 meters. So P is equal to 1,600 kilonewton. Yung 225 millimeters daw is the distance of the tendons from the bottom. So militaw na yung eccentricity natin is equal to 750 divided by 2 minus 225. Take note yung eccentricity natin is the distance from the neutral axis papunta dun sa tendons natin. So ang hinahanap is to determine the axial stress due to the prestressing tendon, and then the flexural stress due to the eccentricity of the tendons, and then letter C is yung flexural stress natin due to the applied load, which is in this case yung 4.5 kilonewton per meter natin. And then letter D is tinatanong yung total stress natin. So pagsasama-samahin lang natin yung letter A, B, and C. So for letter A, so the axial stress is equal to, take note na actual stress natin is equal sa taas man na sa baba, which is always compressive, so depth dapat negative. So the applied force is P is equal to 1,600 kilonewton divided by the area 500 times 750. So that would be 4.2667 megapascal or Newton per mm squared. And then yung flexural stress naman natin galing sa pre-stressing tendons. So PEC over I, so 1,600 times 10 raised to 3 kasi kilonewton multiplied by the eccentricity natin, which is Nagkabaliktad ulit. So 375 is the distance of the neutral axis. And then yung eccentricity natin is 150. And then yung moment of inertia is 750 cubed divided by 12. So that would be equal to 5.12 megapascal. So positive, negative. Kasi magkaiba yung top at saka yung bottom. And then the flexural stress naman due to the applied load MC over I. So para makuha natin yan, kunin muna natin yung moment. So since simply supported lang yan, uniformly distributed, so we can use the formula. The maximum moment at mid-span for uniformly distributed load is equal to WL squared over 8. So using that formula, so 4.5 multiplied by the span is 30 meters squared divided by 8. So that would be equal to 506.25 kilonewton meter. And then apply natin dito sa flexural formula. So 506.25 kilonewton meter. So kailangan natin is Newton mm. So times 10 raised to 6. Times natin ng 1,000 twice. Multiplied by the distance from the neutral axis papunta dun sa pinaka bottom ng beam is 375 divided by the moment of inertia 500 times 750 cubed divided by 12. So positive, negative ulit yan at 10.8 megapascal. So para makuha natin yung letter D, yung total stress natin, so yung force sa top, so kunin natin yung actual natin, which is always negative dahil compression yan, so negative 4.2667 plus yung flexural stress due to the pre-stressing tendons at dahil yan ay nasa taas, so nagkakaroon tayo ng tension, so that would be positive 5.12. And then yung flexural stress due to the applied load is equal to 10.8 negative kasi yan ay compression sa taas. So that would be equal to negative 9.95 megapascal. And then next is yung and then for the bottom naman, so negative 4.2667 pa rin. And then yung flexural due to the pre-stressing tendons natin is negative na sa baba, so 5.12. And then positive na yung flexural stress natin due to the load, positive 10.8. So that would be equal to 1.41 megapascal.